The Earth, our home and a celestial body of immense significance, has long intrigued humanity with its profound mysteries. The scientific understanding of our planet's structure has been a result of centuries of exploration, observation, and research. Today, we know that the Earth is a complex, layered sphere, with distinct compositional and mechanical layers. Welcome to Digital Learning. In this video, we will delve into the structure of the Earth, exploring its various layers and the processes that have shaped our planet. The Earth's layered structure is a result of complex geological processes that have unfolded over billions of years. These processes have shaped the Earth's surface and its internal composition, ultimately determining the planet's geology, topography, and environment. Some of the key processes include differentiation. During the early stages of Earth's formation, it was a molten mass. As it cooled over time, denser materials sank towards the center, forming the core, while lighter materials rose to create the mantle and crust. This process of differentiation established the Earth's layered structure. Next, plate tectonics. Plate tectonics is a fundamental geological process driven by the flow of the mantle. It involves the movement of Earth's lithospheric plates, which cover the entire surface of the planet. The interactions between these plates result in the formation of mountain ranges, ocean basins, and earthquakes. Another process is geological activity. Volcanic eruptions, earthquakes, and mountain-building processes are manifestations of the Earth's internal activity. Magma from the mantle can erupt through the Earth's crust, creating volcanic features, while the movement of tectonic plates can cause seismic events and shape the Earth's surface. Magnetic field generation. The motion of the liquid iron and nickel in the outer core generates the Earth's magnetic field through a process known as the geodynamo effect. This magnetic field acts as a protective shield, deflecting charged particles from the sun and preventing them from eroding our atmosphere. Have you ever wondered what lies beneath the Earth's surface? That solid skin that supports everything from towering mountains to the vast oceans? Well, it's called the lithosphere, and it's one of the most fascinating parts of our planet. Now, digital learners, let's dive into the lithosphere and its components. The lithosphere is like Earth's outer jacket, and it's made up of two main layers, the sial and the sima. Sial stands for silicon and aluminum, and it's rich in these elements. This part of the lithosphere is relatively lighter and less dense compared to sima. That's why you find continents, which are less dense than the oceanic crust, made up of sial. So, when you think of mountains, valleys, and vast landmasses, you're thinking about sial, Earth's continental crust. On the flip side, we have sima, which stands for silicon and magnesium. Sima is the material that makes up the oceanic crust and is denser than sial. When you picture the immense expanse of the ocean floor and the seabed, you're picturing sima. It's the layer that sits beneath the ocean and provides that support for the deep blue waters. Now, you might wonder how we even know that these two layers exist, right? Well, that's where the Geological discontinuity, or the MOHO for short, comes into play. This is like a geological boundary that separates the Earth's crust from the underlying mantle. When seismic waves travel through the Earth, they behave differently as they cross the MOHO. Scientists noticed this phenomenon, and it led to the discovery of this significant boundary. It's like when you're in a pool, and you feel the temperature change as you move from the shallow end to the deep end. That's kind of how seismic waves change when they hit the MOHO. The Geological discontinuity is essentially the division point between the Earth's crust and the mantle, and it's like the Earth's way of keeping its layers distinct and separate. The lithosphere, in all its layered glory, is a testament to the geological wonders of our planet, and it's just waiting for us to explore and learn more. But what about the layer right beneath it? That's the mantle, and it's a fascinating part of our planet that stretches far beneath our feet. Let's explore both the upper and lower mantle, and uncover what makes it such a vital part of Earth's structure. Let's start with the upper mantle. This layer extends from the crust down to about 410 kilometers below the Earth's surface. The upper mantle is like a region of action, where the Earth's geologic wonders come to life. This part of the mantle is where all the action of plate tectonics takes place. You've probably heard of earthquakes, right? Well, they are often caused by the movement of these tectonic plates within the upper mantle. It's like the Earth's puzzle pieces are constantly shifting, colliding, and pulling apart, creating the dynamic landscapes and geological phenomena that define our planet. As you journey deeper into the Earth, you'll reach the lower mantle. The lower mantle extends from about 410 kilometers down to approximately 2,900 kilometers beneath the Earth's surface. In the lower mantle, things get intense. It's incredibly hot and under immense pressure. The rocks here are solid but behave like plastic over long periods. The flow in this region is responsible for the slow but continuous movement of tectonic plates in the upper mantle. It's like the engine that powers the entire plate tectonic system, shaping the Earth's surface. The Gutenberg Discontinuity. Named after the German seismologist Benno Gutenberg, this boundary, often referred to as the G discontinuity, is a crucial geological feature. It is situated at a depth of about 2,900 kilometers beneath the Earth's surface, marking the boundary between the Earth's silicate mantle and the metallic core. It's like a portal to the Earth's innermost sanctum. The Earth's core is divided into two distinct layers: the outer core and the inner core. First, we have the outer core, which extends from the Gutenberg discontinuity down to about 5,150 kilometers below the Earth's surface. The outer core is a region of molten metal, primarily composed of liquid iron and nickel. This molten state is a result of the extreme pressure and temperature conditions that exist at this depth. The outer core is dynamic and responsible for the generation of the Earth's magnetic field, a phenomenon known as the geodynamo effect. The motion of the liquid metal in the outer core generates electrical currents, which, in turn, produce the Earth's magnetic field. This field is essential for our survival, as it shields the planet from harmful solar radiation. Next, we venture even deeper into the Earth's core to uncover the inner core. The inner core is located at a depth of approximately 5,150 to 6,371 kilometers. Despite the immense pressure at this depth, the inner core is solid, primarily composed of iron and nickel. This solid state is due to the extreme temperature, which causes these materials to remain in a solid form. It's like a super hot and super pressurized realm within the Earth, where matter behaves in unexpected ways. The interaction between the inner core and the outer core is fascinating. The solid inner core slowly grows over time, as the liquid outer core provides it with a continuous supply of heat, sustaining the temperature conditions that keep it solid. In this part of the video, let us delve into the reasons why the interior of the Earth is exceptionally hot, exploring the various factors and processes that contribute to this intense heat. To begin with, one of the primary sources of the Earth's internal heat is the planet's formation. When the Earth came into existence around 4.6 billion years ago, it was a molten mass of material. The gravitational energy from the aggregation of particles, combined with the heat generated by radioactive decay of isotopes like uranium, thorium, and potassium, led to the melting of these materials. As a result, this heat from the planet's formation has been preserved within the Earth, creating a substantial internal heat source. Additionally, the Earth's interior is characterized by the presence of molten metal, particularly in the outer core. The outer core is primarily composed of liquid iron and nickel. The flow of this molten metal generates heat, akin to the heating of a metal pot on a stove. In essence, the process of convection within the outer core, driven by heat, plays a significant role in maintaining the high temperatures inside the Earth. Moreover, the Earth's mantle, the layer beneath the crust, also contributes to the overall heat of the planet. The mantle is composed of solid rock, but it possesses a plastic-like property, allowing it to slowly flow over geological timescales. The mantle's heat is generated from various sources, including the residual heat from the Earth's formation, the heat produced by radioactive decay, and the heat released during mantle convection, as it gradually transports heat from the Earth's interior to the surface. Furthermore, the intense pressure deep within the Earth's interior significantly contributes to its high temperatures. As you move deeper into the Earth, the pressure increases dramatically, causing even solid materials to behave plastically and flow over time. This phenomenon, known as pressure release melting, results in the generation of additional heat. So, the scorching temperatures within the Earth's interior are the product of a combination of factors. The heat from the planet's formation, radioactive decay, the flow of molten metal in the outer core, mantle convection, and pressure-induced melting all contribute to the intense heat that resides beneath our feet. This internal heat source not only drives geological processes like plate tectonics but also sustains the Earth's magnetic field, which plays a crucial role in protecting our planet from harmful solar radiation. What about the external structure of the Earth? Good question. To begin with, the Earth's atmosphere is primarily composed of nitrogen, N2, which makes up approximately 78% of the total volume. This abundant gas is vital for life, yet it tends to be chemically inert, playing a crucial role in diluting oxygen and other reactive elements. Alongside nitrogen, oxygen, O2, makes up around 21% of the atmosphere. This oxygen is the breath of life for animals, including humans, as it's essential for respiration. It fuels the combustion processes and is a key element in various chemical reactions. Trace gases, although present in smaller quantities, also play a significant role in the Earth's atmosphere. Carbon dioxide, CO2, is one of the most prominent trace gases, constituting about 0.04% of the atmosphere. While it's in relatively low abundance, carbon dioxide has a profound impact on Earth's climate and is a critical component of the carbon cycle. Other trace gases include noble gases like argon, neon, helium, and krypton. They are present in minute quantities but are important in various scientific applications, such as in lighting technology and as tracers in atmospheric research. Water vapor is another essential component of the atmosphere, and its concentration varies with location and time. It can range from nearly zero in extremely arid regions to several percent in humid environments. Water vapor plays a central role in weather and climate, as it is responsible for the formation of clouds, precipitation, and the greenhouse effect. Particulate matter, including dust, pollen, soot, and aerosols, also exists within the atmosphere. These tiny solid or liquid particles can have significant effects on air quality, visibility, and even climate, as they can scatter and absorb sunlight. Next up, digital learners, we will explore the layers of Earth's atmosphere: the troposphere, stratosphere, mesosphere, and thermosphere, and the hydrosphere, providing a comprehensive overview of their composition and significance. The troposphere is the lowest layer of the Earth's atmosphere, extending from the surface up to approximately 10–15 kilometers in altitude. This region is where weather occurs, and it is characterized by a decrease in temperature with increasing altitude. As air rises through the troposphere, it cools, leading to the condensation of water vapor and the formation of clouds. It is the layer where we live, breathe, and experience the day-to-day fluctuations in weather, making it crucial for life on Earth. Above the troposphere lies the stratosphere, reaching from about 10–15 kilometers to roughly 50 kilometers in altitude. Unlike the troposphere, the stratosphere is marked by an increase in temperature with altitude. This temperature inversion is due to the presence of the ozone layer, which absorbs and scatters the sun's ultraviolet radiation. The stratosphere is significant for its role in protecting life on Earth by absorbing harmful UV rays, thereby shielding us from their adverse effects. Ascending further, we reach the mesosphere, which extends from around 50 kilometers up to about 85 kilometers above the Earth's surface. In this layer, temperatures drop once more, creating the coldest region in the Earth's atmosphere. It's also the layer where meteoroids entering the Earth's atmosphere burn up, creating shooting stars. The mesosphere is a transition zone between the layers below and the layers above, playing a unique role in our planet's atmospheric dynamics. The thermosphere, found above the mesosphere, starts at an altitude of approximately 85 kilometers and extends far into space. This layer is known for its extreme temperatures, which can reach thousands of degrees Celsius. It's the layer where the International Space Station orbits and where the northern lights, aurora borealis, and southern lights, aurora australis, occur. Despite the extreme temperatures, the thermosphere's thin air means it would feel incredibly cold to a human due to the lack of heat transfer. The hydrosphere. While the atmosphere is integral to life on Earth, the hydrosphere is equally vital. The hydrosphere refers to all the Earth's water, encompassing oceans, rivers, lakes, groundwater, and even the water vapor in the atmosphere. Water is a fundamental element of life, serving as the habitat for countless species, a source of sustenance, and a critical component of the Earth's climate system. The hydrosphere plays a pivotal role in shaping Earth's weather patterns and supporting diverse ecosystems. In summary, both the internal and external structures of the Earth are intricately connected, influencing geological processes and climate systems, making our planet a dynamic and unique environment. Understanding these structures is not only a matter of scientific curiosity but also crucial for addressing geological hazards and safeguarding our environment.